Okay, so we're going to be talking about binomial and geometric random variables. What are the conditions for a binomial? What are the conditions for binomial setting? Okay, it's got to be binary. The possible outcomes of each trial can be classified as either a success or a failure. Nothing else. You have to have both of those, success or failure. It's got to be independent. Trials must be independent of each other. If you know the result of one trial does not have any effect on the result of another trial. The number of trials n of the chance process must be fixed. It can't just keep going on. And success, on each trial, the probability of success must be the same. So if you look, B-I-N-S, we're going to be checking our bins. All right? So what is a binomial random variable? What are the possible values of a binomial random variable? Well, a binomial random variable is the count x of successes in the binomial setting. And the possible values of a binomial random variable are the whole numbers 0 to n being the number of trials. What are the parameters of a binomial distribution? How can we abbreviate this information? The parameters of a binomial distribution, n and p, where n is the number of trials and in the chance process, and p is the probability of successes on any one trial. What is the most common mistake students make on a binomial distribution questions? The most common mistake is not recognizing that using a binomial distribution when it is appropriate. Free response questions about binomial distribution are among the lowest scoring questions on the exam. So you need to recognize when a binomial distribution is appropriate. All right? Okay. Determine whether the random variables below have a binomial distribution. Justify each answer. Okay. Roll a fair die 10 times and let x equal the number of sixes. Now remember, we're going to be checking bins. So, is it binary? Yes. Success equals 6 and failure equals not 6. Independent? Yes, it's independent. Knowing the outcomes of the past rolls doesn't affect the outcomes of future rolls. Going to have a chance of 1 through 6 every time. Number? Yeah, we've decided that we're going to roll it 10 times. And successes? Yes, the probability of success is always 1/6. This is a binomial setting. C is the binomial with n equal 10 and p equal 1/6. Shoot a basketball 20 times from various distances on the court. Let y equal the number of shots made. Okay, so we're going to check our bins. Binary, yes. Make a shot. Success is make a shot. Failure is miss the shot. Independent, yes. It's reasonable to assume that making a shot doesn't affect the probability of making the next shot. And number, yes, there are 20 trials. We're going to shoot the basket 20 times. And successes, no. The probability of success changes because the shots are are taken from various distances. So this is not a binary distribution. Observe the next 100 cars that go by and let C equal color. Okay? Binary? No. So we can quit right there. If it's not binary, then we know it's not a binary distribution. There are more than two possible colors. Remember, we have to have two choices, success or failure. And also, C is not even a random variable since the outcomes are not numerical. Okay, check your understanding on page 385. So if you'll stop and check your understanding on page 385. All right, question number 1. You shuffle a deck of cards, turn over the top card, put the card back in the deck, and shuffle again. Repeat this 10 times. Let X equal the number of aces you observe. Okay, so check our bins. Binary, yes. Success is get an ace, and failure is don't get an ace. That should have been an ace. Independent, yes, because we are replacing the card and shuffling each time. Number of trials, yes, we've decided on 10. Success, yes. The probability of success is 4 out of 52 for each trial. Since X is the number of successes, it is a binomial random variable with N equal 10 and P equal 50 seconds. Number 2, choose 3 students at random in your class. Let Y equal the number who are over 6 foot tall. Okay, check our bins. Binary, yes. Success equal over 6 feet, and failure being not over 6 feet. Independent, no, because we are selecting without replacement. So we can really kind of quit right then, but we'll go through it. Yes, there are 3 trials, and yes, the probability will not change from person to person. Actually. Okay, and then 3, flip a coin. If it's heads, roll a second die. If it's tails, roll an 8-sided die. A 6-sided die, roll an 8-sided die. Okay, repeat 5 times. Okay, bins, binary, yes. Roll a 5. A success equal roll a 5. Failure equal don't roll a 5. Independent, yes. Knowing the outcomes of the past rolls doesn't affect the outcomes of the future rolls. And the number, yes, we're going to do 5 rolls. But successes, no. The success changes depending on whether you're rolling a 6-sided or an 8-sided die. This is not a binomial setting. All right, so binomial probabilities. If you are here's our example. In many games involving dice, rolling doubles is desirable. Rolling doubles means the outcome of 2 dice are the same, such as a 1 and a 1 or a 5 and a 5. The probability of rolling doubles when rolling 2 dice is 6 out of 36 or 1/6. If X equal the number of doubles in 4 rolls and of 2 die, then X is binomial with N equal 4 and P equal 1/6. What is the probability that X equals 0? That is the probability, that is, what is the probability that all 4 rolls are not doubles? Okay? So, since the probability of getting doubles is 1 minus, of not getting doubles is 1 minus 1/6, then it's 5/6. So the probability of x equals 0 is the probability of getting a failure, four failures, which is 5/6 times 5/6 times 5/6, etc., or 5/6 to the fourth, which is 0.482. What is the probability that x equal 1? Okay, that means that we have one success and 4 failures. So we can either get a success first and 3 failures, or we can get a success second, get a failure, then a success, and then 2 failures. Or we could get 2 failures, then a success, then a failure. Or we could get 3 failures and a success. So the probability of getting getting the success first and 3 failures is 1/6 times, if you look at all this, 1/6 times 5 to the 6th. Same thing for the success being in the middle, or the second spot, and the third spot, same thing, and the fourth spot, the same thing. So we can add those all up together or multiply them by 4, and we get 0.386. What is the probability that x is 2? Okay, it ends up being that we have 5 times 1/6 squared times 5/6 squared, which is 0.96, and the probability of a 3 is 4 times 1/6 to the third times 5/6, which is 0.015, and of getting a 4 is 0.833. That doesn't sound right. Okay, so we're starting over here with the probability that x equaled 2. That means 2 successes and 2 failures. There are 5 ways to roll doubles twice in 4 tries. So that is 5 times 1/6 to the second, which is our successes, and our failures squared, and we get 0.096. To roll 3 successes, 3 doubles, there are 4 ways to roll doubles 3 times in 4 tries. So we're going to multiply by 4, and we've got, those are our successes cubed times our failures, and we get 0.015. And then to get probability that x equals 4, that means all 4 rolls are doubles. There's only one way to do that, and so okay, that shouldn't say doubles 3 times. It should say you just roll doubles 4 times in 4 tries, and that's 5/6 to the fourth, which is 0.00077. Okay. In general, how do we calculate binomial probabilities? Is the formula on the formula sheet? Okay, yes, it's on the formula sheet, and this is our formula for it. Probability that x equal k is, and I am putting down what this is, okay, stop. Okay, this is our binomial coefficient that we're putting in here, and it's p to the k minus 1 minus p to the n minus k. Thank goodness this is on your sheet, formula sheet. Where n equals the number of trials, p equals the probability of success for each trial, and k is any one of the n values of x. So let's go to the roulette table. In roulette, 18 of the 38 spaces on the wheel are black. Suppose you observe the next 10 spins on the roulette wheel. What is the probability that exactly half the spins land on black? Okay, well, we substitute that in. Remember that we want half of the spins, which is 5, to be black. So we want the probability that x equals 5. So filling in the blanks on the formula, 10 factorial over 5 factorial times 10 minus 5 factorial. That whole thing multiplied by 8, our probability to the 5th, and 1 minus our probability to the n minus k. All right, and when we put that all into our calculator, we get the probability of x equals 5 is 0.2427. What is the probability that at least 8 spins land on black? Okay, well, we can add those up. Remember that when we want the probability of 8, 9, and 10. So we can put all those into that formula. Yikes, what a mess. Anyhow, when we put those all in, remember that that 10 is the number of spins, 8 is the number that land on black, and then that 18 over 38 is our probability. So we add them all up, since it's this or this or this, and when we're done, we get the probability of that x is greater than 8 is 0.0384. All right? Yikes. How can we calculate this on the calculator? I got it on the 84 for you. Go to second bars and go to binomial PDF. And NPK is what goes in there. So we would put this in for 5, 10, probability 18 over 38, and 5 is what we want. And put that in and you're going to get the right answer. If you want greater than, you can use binomial PDF and add those together. Much easier than the formula. Is it okay to use these commands on the AP exam? Well, greater than 8. You can use 1 minus binomial CDF. Okay, so can we use these commands on our AP exam? Writing binomial PDF 10, 18 over 38, comma 5, and 0.2 equals 0.2427 will not earn you full credit for the binomial probability calculation. At the very least, you should indicate what those numbers stand for, that n is 10, p is 18 over 38, and k is 5. But, better yet, write the formula out with the numbers plugged in, then stick it into your calculator, and you'll get full credit. Okay? AP exam common error. When using the complement rule, that's that 1 minus the probability. When using the complement rule for discrete probability distributions, such as a binomial distribution, make sure you identify the correct complement. Notice that when I did the CDF, I used 7 instead of 8. So be careful because you want it less than 8. That's the complement CDF. All right? So just be careful with that. The end.